Hey math fans, Alex here, and in order to conclude chapter 1 of probability theory, I thought I'd give you all some review problems. So in the description, I have linked a document containing a bunch of problems from the chapter that review all the major concepts. Okay, so you'll notice that some of them have one asterisk. That means they're relatively straightforward from the theorems and examples in the book and in my lectures. The ones with two asterisks are more applied problems that involve critical thinking and abstract reasoning. You'll find a full set of solutions, or at least the answers, on the document as well. What I wanted to do in this video is go through 4 problems that I think are so important that have other things going on besides just getting the correct answer that really can teach us something. Okay, so let's get started with problem number 3. All right, so problem number 3 says, a batch of n manufactured items contain k defective items. Suppose m items are selected at random from the batch. What is the probability that L of these items are defective? Okay, so if you want a reference, I would see example 6 that I did. But the first thing that we need in order to figure this problem out is we need to define the event A. And the event A is getting L defective items from a sample of m items from a total population of n items. Okay, so here's kind of the idea. So here's the picture. I have n total elements, 10 total manufactured items, and I could split those into 2 groups. Okay, in the first group, I have k items that are defective, which means that I have n minus k items that are not defective, which I will call normal. Okay, the reason that I bring that up is because from here, we can determine that the total number of outcomes is just drawing m items at random. How many ways can you draw m items at random from a population of n total items? Well, that is just n choose m, which is also equivalent to the binomial coefficient n choose m. Okay, so that is part of our answer. Now comes the more challenging part of this question. Finding the number of ways that A can occur. How many ways can you get L defective items from a sample of m items? Well, for that, we're going to need a different picture. I'm going to draw this kind of big. So this is our total population of n. And what I'm going to do next is I'm going to draw a smaller sample. And this sample is going to contain m items. And we can further break this sample up into 2 smaller samples. Okay, and that's going to be kind of important. So I'm going to partition this in the following way. My first sample, my first small sample, is going to contain L defective items, which is what I want. Well, that means the other part of my sample contains m minus L items that are not defective. Okay, so having a sample of m items where L are defective is equivalent to 2 samples shown where L are defective and m minus L are not defective. So what I have is I have a situation in which you can think of this, as 2 smaller, completely independent samples that combine together to get a larger sample. And then the idea behind that is then you can use theorem 1.3 to get that the number of ways A can occur is the number of ways where the first sample has L defective items, and we have that the second sample, we have the second smaller sample has M minus L normal items. And if we can find both of those, and they're completely independent samples, they're mutually exclusive, theorem 1.3 says we just multiply them together, and that's the number of ways A can occur. Okay. Well, this shouldn't be too bad. In the first sample, how many ways are there to get L defective items? Okay, well, there are a total, if we look back here, there are a total of K defective items, and from that K, I just want L defective items. So that means the number of ways to get L defective items is simply K choose L. From K defective items total, I'm choosing L of them in my sample. And that means that the second sample I can do similarly. From a total of N minus K normal items, total in the population, I just want M minus L of them to be normal in my sample. Okay, so this is going to be N minus K. I'm choosing M minus L to be normal. Okay, that means that the number of ways that A can occur is K choose L times N minus K choose M minus L. That's the second part of my answer. So I get that the probability that A occurs is the number of ways A could occur divided by the total number of outcomes, which is this. And that is my answer. Now, the reason that I chose this problem to kind of work out with is this is the probability distribution. This is the probability for something called the hypergeometric distribution from statistics. Now, we didn't really talk about a lot of distributions. We'll get into a couple of them in a future chapter, but the idea behind a distribution is for trials that are done in a predictable way, you can say a lot about those kinds of trials. And for the hypergeometric distribution, this is geometric distribution, the idea is you have a total population with a certain characteristic, and everyone in the population either has that characteristic or they do not have that characteristic. And you decide to sample part of that population, and you want to know the probability of a certain number of successes in the sample. And this has to be done essentially without replacement, which is what makes it different from a binomial distribution, like flipping a coin. Okay, but I wanted to make that connection, and hopefully that made sense. Let's move on to the next problem. All right, so this problem says 3 cards are drawn at random from a full deck of 52. What's the probability of getting a 3, a 7, and an ace? Okay, so you should pause the video and see if you can attempt this one on your own before I walk through the solution. That's okay, I'll wait. Okay, assuming you've attempted it, this one's relatively straightforward. The event A is going to be exactly as it says, getting an ace, a 3, and a 7. How many ways can that occur? Well, how many different ways are there to draw an ace? 4. So this is number of ways to draw an ace. How many ways are there to draw a 3? Again, there are 4 cards. And how many ways are there to draw 7? Again, 4 cards. So by theorem 1.3, we can multiply those together to get 4 cubed. Now, how many total outcomes are there? Well, what is the trial? What is the experiment? The experiment is drawing 3 cards from a full deck. So how many ways are there to draw 3 cards out of 52? Well, by definition, that is 52, choose 3, which we can simplify in this case since we have actual numbers as 52 factorial divided by 3 factorial, 52 minus 3 factorial. Okay, which if you work that out is going to be 52 times 51 times 50 times 49 factorial divided by 3 factorial, 49 factorial. The 49 factorials cancel. Now we have 52 times 51 times 50 all over 3 factorial. Okay. So then we have that the probability of A occurring, so the number of ways A can occur divided by the total number of outcomes. And when we divide those, we'll get 4 cubed divided by that fraction, 52 times 51 times 50, all over 3 factorial, which is 6. Okay. And that's going to essentially give us 64 times 6 divided by 52 times 51 times 50. And if you type that in, you'll get 0.0029, which is our answer. All right, let's move on to the next one. All right, so problem 8 says, suppose a number from 1 to 1,000 is selected at random. What's the probability that the last 2 digits of its cube are both 1? Okay, so the idea is, for example, let's suppose I took 512 and I decided to cube it. And I'm going to get a really big number. What's the probability that the last 2 digits are both 1? Which in this case, that is not correct, actually. So the probability portion of this question is very, very straightforward, right? The number of total outcomes is clearly 1,000 because there are 1,000 different numbers. And we just have to count the number of numbers when you cube it, the last 2 digits are both 1. The way to do this, however, depends on the kind of background that you have. So this is really what we're trying to find, and if we can find this, we're essentially done. And I argue that really all you need to do is pick a number from 1 to 100 that satisfies this goal, and then you're done. Okay, why do I say 1 to 100? Well, first of all, let's just agree that the numbers 1 through 10 will not work. Okay, clearly if you cube the numbers from 1 to 10, you're not going to end in 11. But that might tell us something. If I cube 1, I end in 1. If I cube 2, I end in 8. Cubing 3, I end in 7. And you can essentially construct a table of cubes. I don't know all of my cubes. I know some of them. It's not really the point for me to show off, but I know that 7 cubed, I don't know what that is. I think it's 343. 8 cubed is 512. 9 cubed is 729. And 10 cubed is 1,000. So if we need the last 2 digits to be 1, there's no chance that any number ending in 2 could do the job. Or any number ending in 3, 4, 5, 6, 7, 8, or 9. So we're only looking for numbers that end in 1. And if you can find a number between 1 and 100 that ends in 1, like 11 or 21 or so on, then 100 plus that number will work. 200 plus that number will also work. So 10, of course, won't work. So you could do brute force if you wanted to, and you could just type them into your calculator. You could just check 0, 1 clearly doesn't work. You can check 11, 21, 31, so on, all the way to 91. But there's a clever solution involving number theory that I wanted to kind of go through with you. This is actually a really fun problem. So what is it that we actually want? Well, let me erase this screen. Well, maybe I'll leave it up. But what is it that we really want? We want a number. We want a 2-digit number whose cube ends in 11. So how would we structure that in the language of number theory? Well, how do we represent a 2-digit number? Okay. Well, a 2-digit number is any number in the form, we'll say, 10b plus 1. It's really 10b plus a, where a is the ones digit and b is the tens digit. Okay, but the reason that I say that a has to be 1 is because we know that the ones digit has to be 1. That is the only possibility. Okay, so that's our 2-digit number, and we need the cube to end in 11. So that means that after cubing this, if you divide that by 11, you have to get a remainder of 0. Actually, that's not totally correct, as we'll see. But let's just go ahead and cube this and see what we get. So if I take 10b plus 1 and I cube it, you could work this out using Pascal's triangle if you want. Binomial coefficients, whatever. You get 1000b cubed plus 300b squared plus 30b plus 1. Okay. Now comes kind of the interesting part. To say that something ends in 11, let's talk about what that means. That's going to mean that is going to mean that the number is congruent to 11 modulo 100. So after dividing by 100, you get a remainder of 11. Okay, so let's look at 211. If I divide that by 100, I get 2 with a remainder of 11. So that's what it means to end in 11. That means when you divide it by the hundreds place, by hundreds, that you get a remainder of 11. Okay, so we can put that into number theory terms in a second. But what I want to do next is I want to note that this number, modulo 100, is congruent to 0. Okay, so note that 1000b cubed is congruent to 0 mod 100. That means if I divide this by 100, I get a remainder of 0, which makes sense because b cubed is an integer. And if you have an integer times 1000, that is going to be some number of thousands. And if you divide that by 100, that goes in evenly. Likewise, 300b squared is also congruent to 0 mod 100. So really what we have is a situation in which this quantity right here, we can say that 10b plus 1 cubed is congruent to 30b plus 1 mod 100. Now, we want this, upon division with 1,000, to have a remainder of 11, which means that we want 30b plus 1 to be congruent to 11 modulo 100. Okay? But that's going to happen by the definition of congruence. That is going to happen if and only if there exists some k integer such that the difference between these two, the difference between those two is divisible by 100, which means this minus this is going to equal 100 times, we'll say, k for some k integer. Okay? But now we're actually almost done, because this means 30b minus 10 has to equal 100k. And I can factor out a 10, or I can just divide everything by a 10, and then I get 3b minus 1 is equal to 100k. And finally, 3b is equal to 100, oh, sorry, I didn't divide the 100k by 10k. So it means that 3b is going to equal 10k plus 1. Okay, why is that significant? There is only one value of b that could possibly make this work, because this side, the right-hand side, that ends in 1. And there's only one multiple of 3 between 0 and 9 that also ends in 1. And that's 7. 3 times 7 is 21, and that is the only possible way that that could end in 1. Okay, so we get b is equal to 1, which is actually a really cool number theory problem, and I just thought I'd kind of bring that up. Okay, so how does that help us with this whole situation? Well, it helps us because the two-digit number that we represented was in the form 10b plus 1. So since b is 7, (10b plus 1) really becomes 10 times 7 plus 1, which is 71. I don't know why that's weird. Okay, so that's 71. Now, if 71 works, that means 171 is also going to work, because the 100 is not going to mess with the ones or the tens digit when you cube it. Okay, so that means 171, 271, 371, all up to 971, which means, okay, what does that mean? Well, it means that we can answer our question, and the number of ways for A to occur is 10. Which means that the probability of A is simply 10 over 1,000, which is 0.01. Okay, let's move on to our last question. All right, so problem 12 says, in throwing 6n dice, what is the probability of getting each face n times? And after you get that formula, use Stirling's formula to estimate this probability for large n. Okay, so forget 6n. First thing that I do in situations like this is I let n equal 1, and then I figure it out. Okay, so then the problem says, then I can reword the problem to say, in throwing 6 dice, we want to know the probability. We want to know the probability of getting each face one time. Well, that's not so bad, is it? What are the total number of ways that can occur getting each face one time? Well, I know that I need to get a 1, a 2, a 3, a 4, a 5, and a 6. I don't really care what the order of those are. Okay, so I'm looking for the total number of permutations of these 6 symbols. So that means that we'll say getting each face one time is going to be my event A. Which means that the number of ways that A can occur is just 6 factorial. Right, so my first roll, there are 6 possibilities because it doesn't matter what the first number is. But then you can't pick that number again, which means there are 5 possibilities for the second number, 4 possibilities for the third, and so on and so forth. Okay, which by definition makes that 6 factorial. Okay. Okay, so how many total outcomes are there? Well, the total number of outcomes, there are 6 possibilities for the first roll, 6 possibilities for the second roll. Okay, so there are going to be 6 to the 6th power since there are 6 different rolls. Okay. So that means that the total probability for n equals 1 is going to be 6 factorial divided by 6 to the 6th power. Does that answer my question? No, but that's a good first step. So this is correct for n equals 1. Let's let n equal 2. This is really good as an exercise to build up to just an arbitrary n. Okay, if we want n equal 2, then we have that the event A is now getting each face, I should have specified exactly twice in 12 rolls, right? 6 times 2 is 12. So in 12 rolls of the dice. Okay, well, how many ways can that happen? Okay, I might go through this one a little bit more methodically. Or I should say rather carefully. So how many ways can A occur? Well, basically I need the numbers 1, 1, 2, 2, 3, 3, and so on until I end with 6 and 6. So I'm going to choose to use, I believe it was theorem, I want to say 1.4, which allowed us to partition this into 6 groups of 2. So that means that the total number of ways this can occur was 12 factorial, right, because I have 12 total rules, divided by 2 factorial, 2 factorial, 2 factorial, 2 factorial, 2 factorial, 2 factorial, or 12 factorial divided by 2 factorial to the 6th power. Right, I'm breaking these up into partitions of 2 each. Okay, and my total number of outcomes is then 6 to the 12th power because I have 12 rolls and each roll has a possibility of 6 outcomes. Okay, so I have that the probability of A occurring is 12 factorial divided by 2 factorial to the 6th power all over 6 to the 12th power. Well, I'm sure you can kind of generalize from here and you see what's happening. 12 factorial is really the same thing as 6n factorial, where in this case n was 2, but for n equals 3 and so on, it works the same way. And then for any n, I can always partition this into, n factorial groups, raising that to the 6th power. Okay, so try it out for n equals 3, right? Then I'm going to want 1, 1, 1, 2, 2, 2, and so on until I get 6, 6, and then 6. Well, how many ways can that occur? Well, I'm going to partition this now into groups of 3. Okay, so now it would be 18 factorial divided by 3 factorial, 3 factorial, 3 factorial, 3 factorial, 3 factorial, 3 factorial. Okay, so whatever the n is, that's kind of your partition. That's how you're going to kind of do that. Okay, so that's only part of it. That's the number of ways that it can occur. And then you'll notice that you're dividing that by 6 to the power of 6n. Okay, so for our final answer, I'm just going to clean this up a little bit. And I'm going to move this up here. So our final answer is going to be 6n factorial all over 6 to the 6n times n factorial to the 6th. And that is our answer. Now, this doesn't help us though, because for large enough n, it's going to be impossible to compute the factorial. But if you'll remember, there's this really cool thing called Stirling's approximation that's going to allow us to do this pretty easily. So if you'll recall, Stirling's approximation said that we can approximate n factorial as the square root of 2 pi n, n to the n, e to the minus n. Really, this term is not so important, but we might as well just include it. For large enough n, it's not that first term isn't going to matter. But it's fine. Let's go ahead and approximate. So this thing is going to be on the order of. Now, let's go ahead and take care of this 6n factorial term. And that is going to be the square root of 2 pi 6n, n to the n, or in this case 6n to the 6n, e to the minus 6n. Okay, so that was this term that I'm going to highlight. And that is going to be divided by 6 to the 6n. Sorry, 6 to the 6n times n factorial to the 6th power, which I can now do in orange. And that is going to be square root of 2 pi n, n to the n, e to the minus n. All right, there we go. So I have to somehow simplify that. Okay, it's not actually that bad. It's more tedious than anything. Okay, so let's kind of figure this out, one tedious step at a time. So first of all, we have the square root of 12 pi n on top. And then we have 6n to the 6n, which I can break up as a product. So this is the same as 6 to the 6n times n to the 6n times e to the minus 6n, all divided by 6 to the 6n times this to the 6th power, which I can break up. So first things first, this square root can be written as, if you'll recall, the square root of a number is just that number raised to the 1/2 power, which means if I raise each side to the 6th power, that's actually just going to get me 2 pi n to the 1/2 to the 6th, which is the same thing as cubing it. Then we have n to the n to the 6th, which is n to the 6n. And then likewise e to the minus 6n. Okay, I believe that's everything, unless I'm mistaken. So now we can start canceling terms out. That cancels with that. That cancels with that. That cancels with that. Right? And then finally, we'll get the square root of 12 pi. We'll say n to the 1/2, all divided by, if you cube this, you have to cube every term. So remember, that's going to be 8 pi cubed n cubed. And then if you really wanted to simplify the exponents, which you're more than welcome to, that's going to be 12 pi over 8 pi cubed times, and then your n term, 1 over n to the 2.5 power. Now, the important thing to note about this is as n approaches infinity, this is a probability, by the way. I just want to make that perfectly clear. This is the probability of you getting each face n times when you roll 6n times. The probability rapidly approaches 0 as n increases. So for n equals 100, you can just plug this in and figure out that it's basically not going to happen. Okay, that's the last problem. Hopefully this was helpful. If you want me to go through any other problems or if you have questions, please ask in the comments. I'm more than available and willing to help you out. But I hope this was helpful, and I'll see you in chapter 2.